the earlier session, we have seen how to design a combinational system, which was a full adder system using Verilog entry. In this session, we'll be seeing a sequential system design, which is a JK flip-flop using Verilog entry. So the module is as shown with 4 input terminals and 2 output terminals. Each port is single bit. So whenever clear is asserted or at the positive edge of clear, Q is reset. So let's quickly create a new project as project 5. Then we'll add a new source as a Verilog module, and here we'll name it as myJK. So module's name is myJK. So let's add the 6 terminals. Having done that, let's declare the inputs and outputs. Since it's a sequential system, we need to define this Q variable as a register. And to realize the functionality of JK flip-flop, we'll be using always block, which will be having sensitivity parameters as clock and clear. So we'll be typing in always at positive edge of clock. So we'll be writing pause edge clock or pause edge clear. So out of these 2 variables, clear will be the first priority to be checked. So here we'll be wrapping every statement declaration in begin and end. And inside, we'll start up with the conditional block, the conditional logic of if and else. So first priority will be to the clear. So we'll be typing in clear if it is asserted. So one can write it as like double equal to 1 or directly as the clear. And then again we'll be wrapping the statements in begin and end. So when clear is asserted, we want our output to be deasserted. So here we'll be using non-blocking assignment. So one can use this way of defining the single bit, or simply one can type in as 0 as logic low. Then for the else part, which is clear deassert, we'll be again typing in begin and end. So when clear is not asserted, we want at every positive edge, depending, like we want the output. We want output in accordance with the inputs of J and K. So here we'll be using key statement with the variables as J and K. Here this forms a 2-bit number, 2-bit variable as J and K. So here we need to declare the possibilities of 2 bits. And then we'll be stating the output, with again using non-blocking assignment. So the first bit is the J and the second bit is the K. So these are the possibilities of a 2-bit number. So since this comprised for K, we'll be resetting it, and similarly we'll be setting for the J as set. One can add the comments as well to increase the readability of the program, to increase the readability of the description. To prevent hardware resets or other issues, one can add the default statement. So this defines the basic overview or the basic block for JK flip-flop. And then for Q bar, one can use the combinational logic, which is just the negation of the variable or the port Q. So we'll be using assign statement or assign block, Q bar as Q, negation of Q. So having done this, so this is the sequential system what we have defined here. So let's quickly synthesize and check the register transfer logic. So synthesis is complete. So let's check the top level module, which looks similar to the main idea what we started with. So let's check the internal blocks in some different time. So now the module is created. So let's test the module by test fixture. So let's switch to the simulation mode later. So here inputs and output possibilities can be changed. So let's define the appropriate inputs to test the module. So as done in the previous sessions, we'll be starting up with the clock 0 and clear asserted. Then after some delay of 100 nanoseconds, we'll de-assert the clear signal, and then we'll continue with the inputs as J and K. So for various values of J and K, the inputs can be changed. Similarly, with some appropriate delay, one can add finish statement, $finish statement. Now for the clock variable, one can use always block with an appropriate delay of 10 nanoseconds. So it's done. So let's switch to the simulation mode and select the test fixture, and we'll quickly check the syntax and then simulate the module. So the output will be available in iSim program as shown. So these are the outputs which are exact in negation, and with every positive edge these transitions can be observed until 100 nanosecond clear was asserted. So let's quickly change the color of output signal. one can verify the functionality, which is the same what we have got for the. So here one can check the functionality of JK flip-flop.